on chapter 8, and then after chapter 8, comes chapter 9. Chapter 9 you'll see is a lot like chapter 8 actually, and that'll be our take-home portion. I'm probably going to give that take-home to you before the break, because I think we just have next week, is that right? And then we come back. But it won't be due until the exam. So I know that you guys have a lot of take-homes, and somebody actually asked me, are you going to give us a take-home to do over the break? Probably will give it to you over the break, but not for you to do over the break. You'll still have a week and a half after we get back to do the take-home. But I'll try to give it to you soon. That way, if you want to do it over the break, then you can. Um, let's do this clicker question. Chandler. Chad stands on a 5-meter long board, so it's 1 meter here, 4 meters here because it's pivoting here, and he has mass 75 kilograms, and Kaisa's mass 60 kilograms. Where can she stand to balance the board? 1 meter to the left of the pivot point next to Chad, a half meter to the left of the pivot point, or can she not balance the board at all? We're looking at our balance of torques. This is just like we did in the lab with the meter stick. Just a little bit different. Folks, sorry. All right, let's stop at about 125, 125. So let's do 10 more seconds. Just guess if you're not sure. 125. All right, let's see. D is the right answer. Remember, we want to balance the torques here. So if I have this mass is 75 kilograms, and I want to put another mass somewhere else in order to balance it, I need to have such that the torques on the left will equal to the torques on the right, or I can think of it as the sum of the torques equals 0. This torque, due to this force, which is 750 newtons, is going to be, what's that, counterclockwise, so it's a negative torque, this torque, and then the other torque, which will be the torque due to Kaisa, which, that's my wife, I don't know if y'all knew that. Did you know that? Yeah. So this torque, we'll call it torque C, will be negative, torque K will need to be positive, and so the sum of the torques will be torque K minus torque C will equal to 0. So I can figure out what is torque K by saying that it's equal to torque C. Uh, so her weight, which is 600 newtons, times R will equal to my weight, which is 750 newtons, times 4 meters. And then you can solve for R. And you find that it's not any of these options. In fact, you can't balance a board like this by standing on this side, which is option B. She can't stand there. And she also can't stand here because she has a force that's less than my force. Right? She has to have a bigger moment arm in order to balance the board. And right now, her moment arm is, a quarter that of the 4 meters. All right? Now follow this. Too early to do these questions? No? All right. Let's let's look at another question. And in fact, this will come up more in chapter 9 as we get more into it. This is sort of the something like the statics that we'll see in chapter 9. And you engineering students will take a whole semester. Let's say that we have a similar system. It's rotating, or it's allowed, it has a pivot point at this point, and I have two kids that are on the seesaw at different places. Hey guys. And I want to know if the man has a mass of 100 kilograms, so M2 is 100 kilograms, and and the lady has a mass of 50 kilograms. I have this radius, I'll call this R1, is 2 meters. then I want to know what is x. So we do this in a similar way. The sum of the torques equals 0. Torque 1, which is due to this force, is that positive or negative, torque 1? Is that torque clockwise or is it counterclockwise, this force right here? You're going to ask yourself the question, this force pulls down, and so that causes the thing to rotate. And what direction is that? That's counterclockwise. So this torque 1 will be positive, right? So torque 1 is positive, and torque 2 then will be negative because it's causing clockwise motion. So this is clockwise, this is counterclockwise, and so my sum of my torques will be torque 1 minus torque 2. Or since it's balanced, you can just sort of forego all of that and say that torque 1 has to equal torque 2. And that's also true. Although on the test, you will need to know which is positive, which is negative. I'll show you the type of problems that we'll encounter where we'll have to figure out the net torque, where you have to consider the clockwise, counterclockwise, but not so important here. If I do torque 1 equals torque 2, that's F1R1 equals F2R2. And then I solve that. R2 we actually called X. I'll put an X right there. We solve that for X. That's F1R1 over F2, which is 50 times 2 divided by 100. Or excuse me, 500 newtons times 2 meters divided by 1,000 newtons. Am I right about that? Yeah. So I just converted these to forces, to weights, by multiplying by g. This is m times g, 50 kilograms times 10 meters per second squared. And then that gives me an x value equal to 1 meter. All right. There's another, we'll see in chapter 9 that there are two conditions for stability, for equilibrium. And this is one of the conditions for equilibrium, that the sum of the torques equals 0. There's another condition for equilibrium, that the sum of the forces has to equal what? What must the sum of the forces for an equilibrium situation have to equal? They have to equal 0. We saw that in chapter 4, right? When we have a static situation, or not even a static situation, but an equilibrium, a non-accelerating situation, that the sum of the forces has to equal 0. So these are two conditions for equilibrium, or for, yeah, two conditions for equilibrium. And so we can also apply that here. So if the mass of the plank is 10 kilograms, I want to know the normal force. Well, let's go back and just label all the forces that we have acting. Actually, they're labeled there. So there's my normal force. I want to know it. And then I have these three forces that are in the negative y direction. So I can do just like we did in chapter 4, where I just say the sum of the forces equals 0, and those sum of the forces are equal to Fn minus Fw1 minus Fw of the plank minus Fw2. And then the normal force is the sum of these three, which is 1,000, or excuse me, 500. That's the weight of the girl plus the weight of the plank. The plank has a mass of 10 kilograms, so that's 100 newtons, plus Fw2, that's the weight of the boy, which is 1,000 kilograms, 1,000 newtons. And so the normal force that acts on the plank will be 1,600 newtons. That's a really simple statics problem. In chapter 9, we're going to see some that are quite a bit more complicated, and we'll just approach some different techniques that you can use on these type problems. And then engineers, in your statics class, you'll have some that are even more complicated from that. All right? Go down from here, y'all. Yeah. All right, let's look at the kinetic energy of rotation, and we're going to use this to sort of leap into determining the moment of inertia for objects, and we'll do some volume integrals and what have you to find that. But first, a kinetic energy has, a rotating body has kinetic energy, and the energy can be related to the angular velocity. So remember, we related angular velocity, which is omega, to v in a particular way. Remember, we said that s, or excuse me, S was equal to theta r, V was equal to omega r, and A was equal to alpha r. So we related our angular and our linear quantities. Think about the units here, right? Omega is 1 over seconds, r is meters, so this gives us meters per second. These are on your equation sheet, but you need to know them for the test coming up after the break. So I can plug this in here. I know that V is equal to omega r, so we can say then that this is 1/2 m omega r squared. Yeah, just 1/2 m omega r squared. So what we're going to do is we're going to take a rotating body and we're going to break it up into a bunch of little pieces of mass. In calculus, what do we call those pieces of mass? Right, it's a dx or a dm in particular. If we're breaking it up into little pieces of mass, we call that our dm, which is our differential element. Y'all talk about differential elements in Calc 1? Yes, no, maybe. Yes, yes, you have, right? You call it that in calculus, differential elements? No? Okay. Well, when you look at a body or when you look at a function and you break it up into little pieces, that's called our differential element. It's the little piece over which you take an integral or with which you take a derivative with respect to. So we're going to imagine our rotating body is made up of a lot of elements, like differential elements, and each element then will have a different linear velocity. Right? If I imagine that I have a disk here, and it's rotating around in this direction, if I have a piece here and a piece here, both of these have a velocity that's in this direction, but the one up here, the one out at a bigger radius, has a velocity that's different from the velocity of the piece that's down here. We saw this in the previous chapter, right? The rabbits on the merry-go-round, the rabbit on the outer edge has a velocity that's bigger than the rabbit on the inner edge. Okay? But how do their angular velocities compare of these two objects? Does this one on the outer edge have a bigger angular velocity, a smaller angular velocity, or the same angular velocity as this one? It's the same, because that's the definition that we have for a rigid body. If we're dealing with a rigid body, remember we said there were two criteria for a rigid body? One was that every part of the rigid body has the same angular velocity, and two was that any 2 points on the rigid body, they don't move with respect to one another. Okay? So they will all have the same angular velocity. Don't turn to the next page, I just want to see what I have here. Give me just a second. Okay, yeah, so we are going to look at the kinetic energy of each of these pieces. We'll derive the kinetic energy for each piece. And relate it to the angular velocity. All right, so let's do that. And then when we do that, we'll come up to a definition that'll be useful for other things. So the kinetic energy is 1/2 mv squared. We know that V is equal to omega r, so our kinetic energy then, as we said, is 1/2 times m times omega r squared. It's just a different way to write our kinetic energy. This, by the way, this term right here is called the rotational kinetic energy. I can also have translational kinetic energy. I'll write it over here off to the side. Translational kinetic energy is if I have an object moving with a certain speed, then it has a kinetic energy equal to 1/2 mv squared. But notice that I can also have materials that have both kinetic energy and rotational kinetic energy. Like, for example, this thing, if I just throw it up like this, what type of energy does it have? Translational or rotational kinetic energy? What type does it have? It has translational because it's moving in a straight line and it's not rotating. But if I take this object and I throw it up like that, what type of energy does it have? It has rotational and translational. So if I throw it like this, it has both. Now you have some homework problems where you have to figure out what is the translational and what is the kinetic energy, and you could see something like that on the test. But it's really a matter of doing the 1/2 m omega r squared. We'll rewrite this in just a bit. And then also the 1/2 mv squared. There's two parts of its energy that you have to add up. All right. So since the angular velocity is constant for each differential element, we can find the total kinetic energy like this. We're going to say 1/2 of the sum from I equal 1 to infinity of mi ri squared times omega squared. So if we go back to our disk, we have a disk that's rotating. We break it up into a bunch of little bitty pieces. In fact, we're going to break it up into an infinite number of pieces. And then for each of those pieces, we're going to calculate m times r squared times omega squared. And then we're going to add up all those pieces. You follow me? Now, this is where our integral is going to come in because we can do that with an integral. We can add up this infinite number of pieces, these little differential elements, and then calculate what is the total. Now, for linear motion, we use the mass to describe the inertia. For angular motion, the moment of inertia describes the inertia of the rotating body. All right, the moment of inertia, we're going to use the variable I to describe it. So let's just sort of recount what we have so far. We said that where we had x, now we're going to have theta. Where we have v, now we're going to have omega. Where we had a, now we have alpha. Where we have, what was the other one? Oh, shoot, what came next? I think force, I think. Where we had force, we now have torque. And where we have mass, now we're going to have our moment of inertia. So as we're going along and we're thinking about translating from the translational or linear quantities to our rotational quantities, now we're going to add this moment of inertia. And it's similar but different from the inertia of a rotating body. The moment of inertia describes how difficult it is to change the state of motion for an object rotating, but unlike the inertia, is not only dependent upon the mass, it's also dependent upon the radius of where that mass is located. Right, so the moment of inertia describes how difficult it is to change the rotational motion of the object. All right, so remember we left off with this kinetic energy was 1/2 times the sum, you've already written this, I'm just sort of writing it over here, of mi ri squared times omega squared. So we're going to define this as our moment of inertia. So I then is the sum from I equal 1 to infinity of mi ri squared. So we're adding up all those differential elements and adding up the quantity m times r squared for each of those different elements. Di then will equal to r squared dm. So if I think about my disk again, remember it's rotating with a certain omega. It has little differential elements in all of these. Now, it has each of these differential elements have a particular mass and they have a particular radius. So the mass of these differential elements is dm, and then each of the differential elements have a particular radius. Okay? When I say dm, That just means the mass of this little piece right here. This little piece also has a certain radius, and this little piece also has a certain moment of inertia. And we're going to define that moment of inertia, di, as r squared times dm. All right? We're sort of working off this basic definition, and this will come up a little later, but this basic definition that I is the sum of mr squared. The moment of inertia is the sum of the mass times the radius squared. All right, so if di is r squared dm, we can integrate both sides, and that leaves us with I here, and this is just going to be the integral of r squared dm. All right, so this will be our basic definition for moments of inertia, and then from this we'll derive particular expressions for the moment of inertia of different bodies. It's probably something that many of you have not seen before, but that's okay. I think that we'll work through it and sort of muddle through it. Now the units for moment of inertia are meters squared kilograms, kilogram meter squared. Right, the meter squared comes from here, the kilograms comes from here. So then the kinetic energy becomes 1/2 I omega squared. And then this will be our expression for kinetic energy. Notice this looks a lot like our translational kinetic energy. That was the 1/2 mv squared. What are we replacing v with omega? And we're replacing our mass with I, our moments of inertia. So this looks a lot like the 1/2 mv squared, but now just in a rotational frame. All right, let's look at some basic particles. So on the test, what you're going to encounter is you'll encounter arrangements of particles like this. When we think of these, I know they look big, but these are point particles or point masses. They don't have a shape to them. They're just really small compared to the system. So we'll just treat these as point masses and not as regularly shaped objects. Later, we'll encounter regularly shaped objects like a bar, a sphere, a cylinder, a disc, a hoop. We'll encounter those type of objects, and we'll treat those a little bit differently. Okay? Well, let's do these first. They're the simplest. I have this arrangement of particles, and I want to find their moments of inertia. Remember I said that our basic definition is I is the sum of mr squared. Or if you want to think of this as an integral, you can think of it in that way too. But it's simpler right now just to think of it as a sum, a summation. What I want to do is I want to add up mr squared for each of these individual particles. I have a 3 kilogram particle at 1 meter, a 1 kilogram particle at 2 meters, and a 2 kilogram particle at 3 meters. So go ahead and take a moment to find the moment of inertia for those 3 particles. You're going to have 3 terms, mr squared plus mr squared plus mr squared. When you do that sort of mini integral by hand, summing up the individual components of the moments of inertia, then you can find the total moments of inertia. Just take a minute. I'll jump in just a second. All right, so usually when we're working with regularly shaped objects, as we'll see in just a bit, we're going to integrate and we'll add up an infinite number of elements. But here we only have 3 elements, right? We have the 3 particles, and so we can just add them up by hand. I have my first particle is 3 kilograms times the radius squared, which is 1 meter squared, or excuse me, not 1 square meter, 1 meter squared, plus 1 kilogram times 2 meters squared, plus 2 kilograms times 3 meters squared. And so this works out to be 3 plus 4 plus 2 times 9 is 18 kilogram meter squared, which is 18 plus 7 or 25. All right, so notice a couple of things that each part contributes to the moment of inertia, but also notice that the smaller parts, do they contribute more or less than the bigger masses? I have 3 kilogram meter squared due to the 3 kilogram particle, 18 due to the 1 kilogram particle, and 25 due to the 2 kilogram particle. So which masses, the big masses or the small masses, contribute the most moment of inertia? The small ones, right? Why is that? Why would a small mass contribute more moment of inertia to the system? Why is that? Why does the small mass contribute more moments of inertia? Because of what? No, not the speed. I mean, look here. What about this 1 kilogram and 2 kilogram mass cause the moments of inertia to be bigger than the 3 kilogram, or I'm sorry, the 18 and the 4 to be bigger than the 3? The distance, right. So it's very important when we have rotating bodies where the mass is located. You ever seen figure skaters or dancers or, I don't know, anybody that sort of moves around a lot with their body? They can change the way that their body rotates a lot by changing where their body is oriented. So if I have my arms out really far, does that cause me to have a big or a small moment of inertia? If I move my mass out to large radii, that causes my moments of inertia to go up. So you'll watch these figure skaters, they'll throw their arms out, and that causes them to spin in a different way. We'll work through that later. It has to do with their momentum. But they change their moment of inertia by adjusting where their mass is located. Okay, so we're going to go through a few derivations. I'm going to have you do this. We're going to have two take-home portions. This one will be a smaller part, and honestly, you can find the derivations online. So everybody should get that. It's going to be a small, maybe 5 points. I'll let you know later. I'll send out an email. But you can find them. I just want you to turn in one of these derivations. I'm going to do one for you, and then you'll do one on your own. Okay? As with take-homes, you can use any resource. You can work together, all that business. It should be a fairly easy way for you to pick up some points on the test. Okay? Um, so this first one, I'm actually going to do two for you, and then you'll do either the third, or the fourth. I think there are four. Oh, no, it looks like there are only three. So I'll do the first two, and then you can do the solid cylinder rotating about a central axis. So the thin hoop is really simple. I have this hoop, mass 1, it's a radius r. It has a total mass m. I can break it in to differential elements, m1, m2, m3. I can continue breaking it into elements all the way out until I break it into an infinite number of elements. The moment of inertia then is going to be the sum of mr squared, which is m1 plus m2 plus m3 plus on and on and on until I add up all the elements. Di then is r squared dm. This is sort of our basic definition. If I integrate both sides, integrate di and integrate r squared dm, then I get I is equal to r squared integral of dm. Why do I take the r squared out of the integral in this case? It's constant, right? As I integrate over dm, that is, as I add up all the little masses, m is not dependent upon r. All of these masses have the same radius, so I can pull that r squared out of the integral. Let me write that in words. So all masses dm have the same radius. As Frankie said, r is constant. It doesn't change with m, so I can take it out of the integral. Okay? And then if I do the integral of dm, that just says I'm adding up all the little mass elements. What is the integral of dm? If I add up all the mass elements in that hoop, what do I get? I don't have ears, do you? No. If I add up all the mass elements in the hoop, what do I get? I get the mass of the hoop, right? So this then will equal to mr squared uh, mr squared. So this is the moment of inertia for a hoop. It's a simple derivation. You use calculus, but you don't really. You can just sort of think about it and get that the moment of inertia of the hoop is just equal to the mass times the radius squared. Now, for a rod and for a sphere and a cylinder, they're not so simple. So let me show you. You've probably never done this. Some of you are in Calc 2, I think. Or actually, no, this doesn't come up till Calc 3. When you integrate over bodies. In this case, it's a one-dimensional body. It's an object that just goes along one dimension. In the next one, you'll actually do 2 dimensions, and it's a little more complicated. All right, so let's do the uniform thin rod. It has a mass m. It has a length L. So I already set up the coordinates going from minus L over 2 all the way to plus L over 2 because I've set this point to be x equals 0. And you can do that. You can do whatever you want in this case. It has a mass m. I break it into differential elements. And so here I've just highlighted the differential element. Right here, this is my differential element. It has a mass, dm, and it has a length, dx. And it's also a distance x from the x equals 0, from the origin. So I start with my definition, di equals r squared dm. And I'm going to change my r to x because that's really what I'm dealing with here, dealing with r equals x. So I say I then is the integral of x squared dm. All I've said there is that really my r is equal to x, that I'm just calling it x here. Okay, now this is the tricky part, and this is always the tricky part in these integrals, is defining what dm is. That is, I need to define dm as some function of x, because I have the integral of x here, but it's with respect to m. And so I need to find some way to define dm in terms of x. And so I'm going to do that like this. I'm going to say that dm is equal to the mass over the length times dx. This m over L, we call this a linear mass density. Linear mass density, it is the mass per unit length for this rod. And if I multiply a length of the rod times the linear mass density, then I'll get the mass of that particular little section. It's kind of like volume density, right? Volume density is mass per unit volume. And if I multiply the volume times the volume density, then I get the mass of the object. So it's just a little tool that we can use when we're dealing with one-dimensional objects like this bar. You can also look at the units, right? This kilograms per meter, that's the m over L, and then dx is meters, and it leaves me with the same units for mass that I need. Right, now I do the integral, x squared m over L dx. I can take the m over L, which is a constant value, take it out of the integral, and I get m over L, the integral of x squared dx. Now the next tricky part is figuring out what are my limits of integration. What are going to be my limits of integration for this integral? Well, I'm integrating over dx. So look back at our figure. What are the limits for dx? Or what are the limits really for x in this figure? That's right. It goes from one end of the rod to the other end of the rod. So it goes from negative L over 2 all the way to L over 2. And so this looks like this. I'm going to put in this limit of integration, minus L over 2 to L over 2. Remember that the integral of ax to the n dx, that this is equal to ax to the n plus 1 divided by n plus 1. Right, the integral of a polynomial, you'll need to know that. You had to use it for the last test too. So this integral is going to be x to the 2 plus 1, that's x cubed over 3, and then our limits of integration are from negative L over 2 to L over 2. Now I apply those limits of integration, m over L, L over 2 cubed over 3 minus negative L over 2 cubed over 3. Just applying those initial and final conditions. This is, I just plug in the final here, the initial here into this function, and I take the difference in those. If you cube out those terms and take care of your fractions and all that business, then you get an expression that's 1/12 ml squared is the moment of inertia for a body that is a bar rotating about its center. All right. What would happen if you changed where the object is rotating? Like what if instead of having the object rotate about its center, we had the object rotate not at this point, but down at this point? What do you think would happen to the moment of inertia? Would it increase or decrease if I had it rotate at this point? Think it would increase? What do y'all think? Think it would go up? You're right. Why would it go up? Can you explain in words why it would go up? All right. Can you explain in words why it would go up? If I have it rotate not at the center, but at the end, what would happen? The radius would increase, right. I would have mass at bigger radii, and that would cause the moment of inertia to go up. That mr squared business, if I increase r for some of the masses, then that will increase the moment of inertia. Now, we might make that your take-home, to derive this now instead of rotating about the center at the end. I'll send y'all an email. I have to think about it, but something along those lines. Okay? Um, let's do the cylinder, too. Actually, we have a few more minutes, so let's do the cylinder. I know this is kind of dry, but I really like multivariable calculus. I think that you guys will like it too. Like I remember in college, it was one of my favorite courses, to think about three-dimensional objects and to think about how we apply calculus to those three-dimensional objects to figure out certain things. Honestly, you're probably never going to see moments of inertia again, but especially those of you that go into graduate school, you could very well see three-dimensional calculus, multivariable calculus like this again. Being able to integrate over the volume of an object is a pretty useful thing to do. Uh, whether you're dealing with charges or whether you're dealing with masses or whatever it is that you're dealing with, it can be very useful, especially for engineering majors. All right. Um, so let's say that we have a solid cylinder that's rotating about a central axis. It has a radius r rather. It has a length L, and it has a mass m. This is the cylinder looked at from the top, and we're going to break it into differential elements that are going to be annular cylinders. Sort of a tricky thing when you're doing these integrals, that you try to figure out what is my differential element. So in the previous one, we just took the little segment of the bar and we said that's our differential element. But in this case, as we're dealing with a cylinder, we're going to take it, a solid cylinder, we're going to break it up into annular cylinders. So let's say this is our cylinder. We're going to start at the middle, and we're going to have a little annular cylinder that's hollow in the middle, right? That's an annular cylinder, like an annulus. And then I move out further and further, and I'm going to integrate the moment of inertia for each of those annular cylinders. You understand what I mean by an annular cylinder? It's like a toilet paper roll, like the little cardboard roll, the little tube. That's an annular cylinder. And so we're going to break it into those. They'll each have a mass, dm. They'll have a radius, or a width, dr. And then they'll be at a radius r. Now, we need to figure out the density of the cylinder. The density of the cylinder is m over v. That's going to be m over pi r squared times L. That's the volume of a cylinder. And then we want to apply the definition for the moment of inertia. So di is r squared dm. I is the integral of r squared dm. Nothing new here. The new part here now is trying to figure out what is the mass of our differential element. What is the mass of that annular cylinder? Well, dm is going to equal to the circumference of our annular cylinder, that's 2 pi r, times the length of the annular cylinder times the width, dr. This all represents the volume of the annular cylinder. And if we have the volume, if we multiply it times the density, then that'll give us our mass dm. So our annular cylinder, if we want to know the volume of it, we take 2 pi r, that's the circumference of it, and then we multiply it times the length, and then we multiply it times the width. In general, whenever you're dealing with volume, you're going to have three elements, three mass elements. You multiply all three together, and you'll get the volume. I know this seems a little obtuse to you right now, does it? That's okay. I'll show you some others, and then for the take-home, you're not going to see this on the actual exam, only in the take-home. I don't really want you to master it. I'd love for you to sort of have a familiarity with it, but you don't have to master it. That's why I'm giving it as a take-home. Okay, folks? You good with me? I expect everybody to get the full credit for this. It's just going to be an exercise for you to do. Okay, so dm then is, I can integrate this, integral of r squared dm. So now I'm going to put in 2 pi r L rho dr, just substituting in that for dm. And now I have an integral for dr that will look like this. It's going to be 2 pi L rho, 2 pi L rho, the integral of r cubed dr. And that's an integral we can do. This is going to go from 0 out to big R. That's our limit of integration. Because I'm integrating, I'm starting in the middle, and I'm going out on these annular cylinders as I go along. And so this is going to be 2 pi L rho r to the fourth over 4. Now I have an expression for rho, 2 pi L m over pi r squared L. This is just the density that we did before. And then I have r to the fourth over 4. Get some things cancel here. Our pi's cancel. Our l's cancel. Notice the moment of inertia as it rotates about this axis down through the center doesn't depend upon the length of the cylinder. That doesn't matter, only on the radius. 2 cancels here and leaves a 2 there. And I get an r squared cancels there. And I get 1/2 mr squared. That is the moment of inertia of a cylinder that rotates about its central axis. You can do that for all sorts of different shapes, integrating in various ways, and you get these. Now you'll have this table on your equation sheet. It is on your equation sheet, in fact, and it gives, here's the hoop or radius of radius r, mr squared. That was that first derivation. Here's the thin rod of length b rotating along an axis through its middle. And here's the cylinder. This is the one we just did. You can also do a cylinder of radius r and length b, rotating about this axis. So, like for example, this one would be me rotating like this, and then this one would be like a forward flip, or maybe a cartwheel you can think of. And then here are some spheres, a solid sphere and a thin-walled hollow sphere. We're going to use these next time, and you'll see why you have this table. They'll come up in some problems when we get into Newton's second law. Okay, people? How are we feeling about this? You sort of look a little bit afraid. Are you okay? Yeah, don't sweat it too much. I know that's a lot to throw at you and some stuff that you haven't seen before, but I'm going to do it as a take home. You'll be able to find resources to help you along the way. And if you have trouble, just come see me. I'll help you with the derivation too. All right, well, let's stop there. It's a little early, but let's stop there. I don't want to get into this next bit. It's going to take a while. Okay? Y'all have a great day. Let me know if you have registration issues. And happy birthday, Charity. Good day.